Okay, our next speaker is Harish Guruprasad. Dr. Harish is a assistant professor at the Computer Science and Engineering Department at IIT Madras. His primary areas of interest are in machine learning, statistical learning theory, and optimization. So before joining IIT Madras, he was previously a research scientist at IBM Research Labs and was also a postdoc at the University of Michigan. So he completed his PhD at the Computer Science and Automation Department at Indian Institute of Science, uh, and then joined IIT Madras a couple of years back. Yeah, so today he's going to talk us about some simple to complex objectives in classification. Yeah, Harish, you can take over.
Hello everyone and good evening. So can you all hear me and see my slides? Arun, can you just confirm whether you can hear me and see my slides?
Yes.
Okay. Yeah. So thanks for attending my talk, everyone. So I hope you've had a great session so far and continue to have today and the next 2 days. So the objective of, the title of my talk is simple to complex objectives in classification. So I'm hoping that at least some of these terms are familiar to you. I'm hoping that you know what classification is, but even if not, I'll try and explain what it is. So the crux of this talk is going to be what are really simple objectives and why do we need complex objectives? And you will see the transition from the algorithms which have simple objectives to algorithms which actually are helping in solving complex objectives, right? So we'll do that. So the details of the algorithms are not so important. It is more important to get what kinds of problems are being looked at in machine learning right now, right? So that's the main goal of this talk. So if you don't get the math symbols behind some of these things, don't worry too much about it. Just try to get the examples so that you can always look up later on what these things mean. Right. So, yeah. So this is a broad overview of the talk. So it's just the first section is really simple tasks in machine learning. The second section is complex tasks. So before we explain what complex tasks are, we must explain what simple tasks are. So that's what I'll do in the first part. So we'll be working in the standard supervised learning setup. I hope you know what supervised learning is. So this is the most classic example of machine learning. And pretty much whenever anyone says machine learning, this is the default paradigm people mean. Of course, the other paradigms like unsupervised learning, reinforcement learning are also popular. But this is the standard paradigm when someone just says machine learning, this is what they mean. So what does this mean? So let's take the standard example for supervised learning, which is, say, multi-class classification. So what is multi-class classification? So this is the assumptions that you make for solving a problem, multi-class classification problem. Right? So you might have, let's say, images coming from some distribution. Right? So you might have images coming from some distribution. So that's the instance. You have an instance taking values in the space of images. Say drawn. These need not be images. Images are just an example here. So let's say you have images coming from some distribution over images. Right? And for each image, you have a distribution over labels. So that's, say, let's say in this case, you have 3 possible labels. It's either a mountain or a cloud or a sky. Right? So these are the 3 possible labels. For each image, you have a distribution over labels. So note that I'm saying distribution over labels are not a given label. Why is that? Because some images, it is not really clear it is a mountain or a cloud or a sky. For example, the first image, it is labeled mountain, but some might, if you give it to some other person, he might actually label it as a sky or a cloud. Right? So it is quite possible that there is inherent uncertainty in the labels. So that's why I wanted to give this kind of simple example where you can immediately see that you cannot really quickly label something as a mountain or a cloud or a sky. I mean, of course, the third image is clearly just a sky. And the first image, some might label it as sky. And that's what is visible here in the first example and fourth example. They are the same image, but they are labeled mountain and sky. Right? So someone might label it sky instead. So that's why I said that there is inherent noise. And that is kind of modeled by saying that the label it's distributed over the label space as some distribution P, right? So that's, let's say in this case, just 3 possible labels are out there. So for each image, you have a distribution over the 3 labels. So that's just a simple example to keep things in track. So this is the case. And what's the task? So you have data like this. You have data like image 1, mountain, image 2, cloud, image 3, sky, image 4, sky. You have data like this. What's the goal in supervised learning? The goal in supervised learning, at least in multi-class classification, is to learn a classifier which takes in an image and outputs one of mountain or sky or cloud. So that's the goal. Right? You have to learn a classifier which does that. And what should it satisfy into? Right? right? So that's so in this case, we'll ignore the notation so much, but you can immediately see what's happening here. The instance spaces are the images here, and the set of classes or the set of labels that you see on the images correspond to sky, cloud, and mountain, and the set of predictions that you make are also sky, cloud, and mountain. Right? So that's y and y hat. You'll see the difference between y and y hat soon, but for now, we can see what these x, y, and y hat mean. Okay. So what's the setup? The setup is you can assume that there is a distribution D over the instance and labels, and then you have samples drawn from the distribution. And then the goal is to return a classifier which takes in an instance and outputs a prediction. Right? So that's the goal. Right? We'll make some simple abstractions, don't worry. So here comes the key question. Right? How do you evaluate? Let's say you have an algorithm which outputs a classifier. How do we evaluate the classifier? Right? So that's the key question we want to ask. And for example, something you might say, well, I'm going to use accuracy. Right? So what accuracy? Accuracy is a pretty simple evaluation metric, and it's captured by this matrix here. What does this say? It says that if the true class is sky and you predict sky, you get 1 point. Right? If the true class is sky and you predict mountain, you get 0 points. If the true class is sky and you predict cloud, you get 0 points. Right? Similarly for mountain and cloud. Right? So that's you can get points for the classifier gets points for each data point, and obviously it has to increase the points as much as possible. So that's an evaluation metric. But is this evaluation metric the right evaluation metric for every kind of problem? For example, you can easily imagine a situation where you are building a movie star rating algorithm, right? So the algorithm has to take in a movie, maybe it takes in movie reviews or movies itself, and rates them as either 1 star or 2 star or 3 stars. That's what it does. So in this case, it is not natural to have the same matrix here, right? I mean, imagine instead of sky, mountain, and cloud, if we had 1 stars, 2 stars, and 3 stars here, right? That's not a really good way of evaluating. So this is a much better way of evaluating, where this is what you say. If truly the movie is 1 stars and you rate it as 1 star, you get 2 points. If truly the movie is 1 stars and you rate it as 2 stars, it's bad, but not as bad as 3 stars, so you get 1 star instead. If truly the movie is 1 star and you rate it as 3 stars, you get 0 points. So this is to get a sense of how wrong you are. Then here the main thing to notice, there is obviously the perfect prediction, but not all mistakes are equally wrong. That's the key thing to note here. So if the true number of stars is 1, predicting 2 stars and 3 stars both are wrong, but predicting 3 stars is more wrong than predicting 2 stars. Right? So this is a more natural evaluation metric for this kind of problem. So you can even have problems where the set of predictions is different from the set of classes. For example, you might have a system which takes the same problem as before, classifies the images as either sky or mountain or cloud. But you can also have a situation where the classifier can just say, I don't know. Right? So that's the question mark here. And how do you incentivize the classifier to predict, I don't know? You give it half a point. Right? So half a point is greater than 0, but it is less than 1. So it would ideally predict, say, it would say, I don't know, if it is not confident in one of the classes. So, and this is something which is a desirable character. I mean, for this problem, it's not so much, but imagine this was a medical diagnosis problem where you have to diagnose between, say, lung cancer, common cold, and emphysema, and I don't know, right? So in this case, it would be nice for a classifier to say, I don't know. It's more important to have a measure of uncertainty of the classifier than to get the whatever diagnosis that you can get. So this is another example to just illustrate that the set of predictions can be different from the set of classes. But that's just an example. Let's just move on. In general, you might have an utility matrix. Right? So what does the utility matrix say? The utility matrix, it's an n cross k matrix where n is the number of classes and k is the number of predictions. And the utility matrix would just say how many points would you get if y is the truth and t is the prediction. So that's captured by u of y command. So that's utility matrix. Okay. So, well, now you have this utility matrix. You can ask what is the best possible answer that you can get. And there is a name for that. And the classifier that does the best for a given utility matrix is called the base classifier of a utility matrix. So here's the definition. Where I'll just read it out. The base classifier for a given utility is the classifier that maps every instance to the prediction incurring the smallest expected loss. So if you don't understand it fully, don't worry about it. So here's just the example for the multiclass 0-1 laws. So the multiclass 0-1 laws or the accuracy is the same thing. So for the case of accuracy, what's the best classifier? The best classifier is obviously what it does is the classifier which takes a look at the probabilities of, say, for example, sky, mountain, or cloud. It takes a look at the probabilities of sky, mountain, and cloud. Let's say if it is, say, 0.5, 0.2, and 0.3, and it just predicts the class with the maximum probability. In this case, 0.5 is maximum, so it might say sky is the class. Right? So that's the base classifier. So base classifier is pretty intuitive notion. So and the key thing to note is depends on what utility you're using. So it will change if you're using a different utility. For example, here is an illustration of the classifier, base classifier for 3 different utility matrices. So this is the standard accuracy utility matrix. For that, the base classifier simply just partitions the probability space into 3 symmetric parts. So what is this triangle here? The triangle indicates the probability space. So 100 indicates sky, 001 indicates mountain, 010 indicates cloud. Right? So that's sky, cloud, and mountain, or sky, mountain, and cloud. So these are the 3 extremes, and anything in between is some kind of randomness between the 3. Right? So that's captured by the area in the middle of the triangle. So, and what the base classifier for this particular utility matrix does is symmetrically partition this triangle into 3 pieces, and that makes sense. Right? So in this case, it says this region corresponds to predicting mountain, this region corresponds to predicting sky, and this region corresponds to predicting cloud, and so on. You can see that for the star rating case, which corresponds to what is called as ordinal utility, the base classifier changes. You can see that the region for predicting 2 is significantly larger in this case, and that kind of makes sense, right? So why is that? Because for when you predict 2 stars, it's kind of hedging the bets. It is so it's more optimal to predict 2 in more situations. That's what is captured by here. Of course, if you're still in a situation where the movie is clearly 1 star, you have to predict 1 star. But if you are in a certain degree of uncertainty, it might be good to predict 2 stars rather than 1 or 3. That's what this utility is saying. And similarly, you can have the same thing for this utility also. This is called the abstain utility. So this is just a conceptual idea. This is called the base classifier. Let's move on. So, okay, now this is just a conceptual idea. How do we get there, right? So the main problem in getting the base classifier is that the base classifier requires you to know the probabilities. Right? So I said that, well, how do you get the base classifier? You just ask for an image, what is the probability of sky, mountain, and cloud? And if you have 0.5, 0.3, 0.2, you say sky. But where are you getting these 0.5, 0.3, 0.2s from? Right? So that's not clear. And you can do that using standard probability estimation techniques using training data. That's what is called plug-in classifiers. So you estimate the class conditional probabilities using standard methods, and then you use the base classifier to make the prediction. Right? So you can do that for pretty much any utility matrix. So the base classifier is possible to achieve for well, at least you can get close to the base classifier if you have sufficient data. Right? So that's why I'm going to call these problems, utility sensitive classification problems, as simple classification problems. Recall the title was from simple to complex. So these are simple problems mainly because there is at least in principle a way to get the right answer. The right answer is the base classifier, and there is in principle a way to get the right answer. So that's why these are called simple problems. Fine. So, but well, the title was simple to complex objectives. Right? So what's a complex objective? Right? So we'll do that now. So what's the main problem with simple, what's the main pitfall with utility sensitive classification or simple objectives in classification? The main pitfall is kind of obvious. That is, you need to know this utility matrix to actually even start to give a classifier. And it is not really practical in many situations because you don't know the utility matrix a priori before you start solving the problem. It is, for example, you might not know the importance of each class, or you might want to achieve the best accuracy possible under each class. Right? I mean, these are all various scenarios where you don't know the utility matrix beforehand. For example, let's say you have a situation where you want to build an image classifier, but some people might value dogs more, some people might value cats more, some people might value, say, horses more, some people might value tables more. So it is quite possible to be in a situation where class importances are different for different people. So how do you, I mean, let's say you are Google. In that case, you want to build a general image classifier. You don't want to build you want to cater to everybody, right? So you don't want to just maximize accuracy, or you don't want to really set a utility matrix, because that's not the utility matrix that everyone shares. And there are several other situations. For example, let's say you are trying to build an object detector from radar signals, and you want to predict whether there is an enemy aircraft or not. Here, once again, it's not immediately possible to say what the utility matrix is. There is a risk to false alarms. I mean, if you predict that there is an ICBM coming and you launch a nuclear warhead, and then you find out that that was really a false positive, you have doomed the Earth to a nuclear winter, right? So that's the at the same time, if you don't you miss an ICBM coming at you, that's also pretty bad. That's also a bad situation. So these are situations which are high risk, and it's not really possible to give a utility matrix beforehand. In such situations, are not really a good place for utility sensitive classification. So these kind of objectives are not well expressed using utility sensitive classification. So can we expand this more? So the standard way to expand this, and this still does not cover every scenario, but this slide is just to let you know that utility sensitive classification is a useful tool to have in your toolbox, but that does not capture all kinds of classification problems. Right. So what I'm going to propose is that we expand the set of problems a little bit more. So what kind of performance evaluation metrics can we solve? So here is a fundamental object that is associated with every classifier, which is called the confusion matrix. So confusion matrix is a very fundamental object associated with every classifier, and we are really going to focus on performance metrics that make use of just the confusion matrix. So what is the confusion matrix? For people who don't know, I'm just going to give like a brief example. Let's say you have a simple 3-class problem here, right? So you have 3 classes: the orange class, the green class, and the purple class. And these are it's a one-dimensional instance space. So you have the orange class is Gaussian with the center at some point, and the green class is also Gaussian with some other center, and the purple class is also Gaussian with some other center, right? So this is the situation you have here. And let's imagine this particular classifier. So this particular classifier highlighted here, which essentially says everything that is less than a given quantity is orange, everything that is greater than a given quantity is purple, and everything between that is green. This is a reasonable classifier to have, and you can compute the confusion matrix of this classifier this way. So what does the confusion matrix say? It's once again it's a matrix here. You can see that. Let's first try to understand the first row of this matrix. What does the first row say? Let's look at the orange row. The orange row says that the first column of the first row says how much fraction of orange is classified as orange, right? So that's 0.7 by 3. So we'll come to the by 3 later. So 70% of orange is classified as orange according to this classifier. So that's 0.7. How much of orange is classified as green, right? So you see that this region is classified as green, but there is still possible that it is orange. So about 20% of orange is classified as green. And we can ask the final question, how much of orange is classified as purple? And that's about 10%. That's 0.1. So I have a by 3 here because we are trying to match each row to sum to the class probabilities of orange. So in this case, they are equally probable. So it's 1 by 3. So that's 0.7 by 3, 0.2 by 3, and 0.1 by 3. That corresponds to the first row of the confusion matrix for this classifier. Similarly, you can do the same thing for the second and third row, and you can get a confusion matrix out. So the confusion matrix is a very fundamental object that's associated with every classifier. And what we'll be focused on is evaluation metrics that use the confusion matrix. Okay, so that's the generalization we are doing. So that's the generalization. We are looking at performance metrics of a classifier that are a function of the confusion matrix of the classifier, where this phi is some reward function, right? So that's the goal here. And this is strictly more general than utility sensitive performance metrics, because if you use your phi to be a linear function, then this reduces to the utility matrix, utility sensitive classification problems. If you had more general functions, you would have maybe quadratic functions, or even logarithmic or exponential. You could have more general functions than linear. If your phi was more general than linear, then you cannot express such performance measures using utility sensitive performance, utility sensitive matrices. Right? So that's the generalization we are doing. So is this needed? Why do we need this? And the first thing is that this is not new by any means. And a lot of classic performance measures cannot be expressed as utility metrics. So for example, the classic F measure, which is used for trading of precision and recall. Don't worry if you don't understand what these things mean. You just need to know that these measures of evaluating a classifier are pretty common. Right? So that's the F measure. And you can see that this cannot be expressed as a linear function of the confusion matrix. So the C's are the confusion matrices and these elements are, so you can see that here, it's not possible to express this as a linear function. Let's look at, there are several examples. Let's just look at the simplest example here. Let's just look at the simplest example, which is the minimax reward function. So what does this say? I mean, let's try to understand that. So P of C is min over I, CII by pi I. So pi I is basically the fraction of class I instances. So for example, in the previous case, we had pi 1 equal to pi 2 equal to pi 3 was 1 by 3. That was the situation we were at in the previous example. So what does this tell you, right? So it asks you to maximize the minimum accuracy. Right? So I is the number of classes. So here it intrinsically trades off all classes. So even if you're achieving 100% accuracy on the sky class and 100% accuracy on the mountain class, but you're achieving, let's say, only 20% accuracy on the cloud class, your minimax phi of C would say just 0.2. Even though you're achieving 100% accuracy on the sky and mountain classes, the cloud class you're achieving only say 20% accuracy. That means that your P of C would say just you're only 0.2 good. So that's not immediately you would have a classifier which is penalized for focusing too much on say 2 of the 3 classes and neglecting 1. So this is going to force the algorithm or whatever algorithm we design to focus on all the classes. So this is the kind of things that you can make the classifier do if you go beyond linear functions. Right? So that's the main takeaway here. So I think I'll skip these 2 parts and we'll move to what we can do. Right? So the main contribution here is that you can actually convert this problem, which is you want to maximize over all classifiers your phi of the confusion matrix of H. That's what you want to do. You can really convert this to a finite dimensional optimization problem. So what is this problem? So this you can just create the set of all feasible matrices as confusion matrices as this. Right? So what does this mean? Let's take an even simpler problem. You have just 2 classes. Right? So you have these 2 classes. This is the negative class is orange and the positive class is, say, let's say, purple. So you can have the most natural classifiers here are simply thresholds, right? So you can say everything to the right of a point is purple, everything to the left is orange. So you can imagine this is classifier 1, this is classifier 2. So each such classifier has a confusion matrix. So the confusion matrix is, in this case, it's a 2x2 matrix, but let's just focus on the diagonal elements, right? So we have 2 classes. So the confusion matrix is actually 2x2, but let's just focus on the diagonal elements, which we'll call as true positives and true negatives. And ideally, you want to maximize these 2 numbers. Right? So that's, let's go back to the confusion matrix definition here. Right? So in the confusion matrix definition, what is the best confusion matrix? Right? So what's the best confusion matrix? Obviously, you want the diagonal elements to be as high as possible. Right? So the diagonal element for orange should be 1 by 3, green should be 1 by 3, and purple should be 1 by 3. Everything else should be 0. That's the ideal confusion matrix. But of course, in this case, it is not possible to even achieve that confusion matrix. So that's the rub here. We'll come to that soon. So let's take the simpler 2-class example. So you have a 2-class example here, and let's consider these 2 classifiers. Right? So the classifier 1 seems like a very intuitively natural classifier, which kind of just says everything to the right of this point is purple, everything to the left of this point is orange. And this classifier happens to achieve a true positive and a true negative numbers of 0.42, 0.42. Then you can ask the question, okay, what about this classifier, which classifier 2, which is going to get almost all of the purple correct, but going to miss a lot of the orange. Right? So that's that classifier would actually achieve a true positive and true negative of 0.25, 0.49. That's captured by this point. Obviously, you can try different classifiers and you will get different points on this true positive, true negative plot. And if you tried that, this is the shape that you would get. These are the possible true positive, true negative values that you can get. Note that you can never really get 0.5, 0.5. So 0.5, 0.5 is off the table. You can't even get that. Whatever classifier you use, you can't get 0.5, 0.5. Right? So that's the structure of this particular problem. So, and once you've done this, you can use tools from optimization to actually solve this problem. So I'll not really go into the details of that so much, but this is the key idea. The key idea is that once you've converted this classification problem into an optimization problem, then you can use standard tools from optimization theory to solve this. So I'll not really go into the details of this because I think we are over time. I'll just skip this. So that's one measure of complexity. The complexity in the sense that you have objectives which are more complicated than linear. Right? So linear corresponds to standard utility sensitive classification problems. You can do more complex than measures than that using tools from optimization theory. But what is one other notion of complexity which is very prevalent these days? So those are where you have classification. Your goal is still to say learn a classifier, but not all classifiers are acceptable. You constrain your classifiers to satisfy some properties. So where would this make sense? Right? So let's consider a future scenario, right? So where a student is desired to be admitted into IIT Madras based on a full feature vector, let's say individual marks, recommendation letters, and so on and so on. So the objective is to admit students who will turn out to be successful graduates. That's the goal of such a scenario. Right? Let's make some standard assumptions. What does a machine learning system do? Right? So what a machine learning system does is it uses all past data and says, okay, here is one student who had so and so marks, so and so recommendation letters, and so on, and he went on to succeed in life. Let's say he went on to win a Nobel Prize, right? And you might have several such data points. You might say this person did not succeed as much as you would like, or you might have several such data points, and you might want to use this to build a model that looks at a given student data and decides to admit him or not based on how successful they will be or how useful the education process will. Of course, this is a finite resource game, so you have to take that into account. So such a system has multiple objectives other than maximizing just the fraction of successful graduates. Right? I mean, if you want to do that, you can admit everybody. Right? So you could do that, and you will maximize a lot of total successes. But that's just not possible because the total student intake is constrained. So you cannot admit 1 million people into IITs. That's just not possible. So what you can do is you have these extra constraints to the classifiers. The total student intake is constrained, so it must have, let's say, a preset percentage of students to admit. Right? So that's one simple constraint. Or the government might say mandate other constraints also. It might say that look, the fraction of girls and boys is very different, so we mandate that the fraction of girls admitted match the fraction of boys. I mean, so it's possible the government can come up with constraints, and the goal of machine learning is not to come up with these recommendations, but rather if someone comes up with these recommendations, how do you implement this? Right? So if you have a machine learning system, how do you design a classifier which comes up, which can satisfy these constraints? So these are natural constraints. I mean, if you just said I wanted to maximize accuracy, you might just go ahead and admit just say, let's say, the top 100 boys in some IIT coaching center, and that might work. Right? But that's not going to satisfy the constraints. So that's the and this is a very simple example, so that it was really tailor-made for IIT students. But this actually is a very real practical problem, and this is just an example. Right? For example, this is a real problem in say in policing systems, where in the US they found that there is very real difference in the way parole is given to, say, white prisoners and black prisoners. So because the parole system, there is a computer system which decides whom to give parole to, and by having a system which violates, which does not satisfy very natural notions of fairness, there is an inherent rip in the social fabric. Right? So these are more important things to satisfy than just accuracy. So these are very natural constraints that someone can come up with. And how do you now design classifiers which not only do well on the training data, but also satisfy these constraints? So once again, the key idea is that to note that these constraints can be converted to constrained optimization problems. Let's say, for example, let's take the total number of students must be kept to some fraction, right? So that's the intake, right? So y and y hat is the same thing that we had before. Y is the set of truths and y hat is the set of predictions. So you have the true negatives, the false positives, false negatives, and true positives. Right? So what do you want to maximize? You want to obviously maximize the accuracy. Well, that's not obvious, but let's say you want to maximize the accuracy. So you want to maximize the true positives plus true negatives. But you can, let's say you can only admit 25% of the students who are applying. And so that's a constraint now, which means that the true positives plus the false positives has to be less than 0.25. So and you can convert this into an optimization problem, which essentially turns out to be this. You want to say maximize over your set of feasible confusion matrices, C00 plus C11, subject to this constraint of C01 plus C11 is less than or equal to 0.25, which essentially corresponds to maximizing your accuracy over this, the lower part of the shaded region. And what's the use of this? The moment you have converted these constraints, real world constraints, into mathematical form, and you have framed as an optimization problem, once again, you have all the tools from the optimization literature at your disposal, and you can solve these problems. So let's have the slightly more complicated example where, let's say you want to say that the total fraction of girl student admitted must match the total fraction of boy students admitted. So let's say you have that constraint. Once again, the goal is to maximize accuracy, subject to satisfying these constraints. So what is the accuracy? You have now, in this case, you have two confusion matrices. You have a confusion matrix on girl students and a confusion matrix on boy students. Right? So you can say that once again you want to maximize the accuracy, which means that so true negatives on girls, you want to maximize true negatives plus true positives on girls and true negatives plus true positives on boys, subject to the constraints that false positives on girls plus true positives on girls is equal to false positives on boys plus true positives on boys. Right? So that's the constraint that you have, and this kind of constraint is called demographic parity. And how, once again, framing a problem like this in the optimization language helps us to use tools from standard optimization literature. So we can do that, and so we can use standard tools from Lagrangian theory and solve these problems. Yeah, I'm not really going to go into the details of this. So that basically finishes the things that I wanted to say. Yeah, so I think that's done. Yeah, if you have questions.
Thanks, Harish. So there are a couple of quick questions because we are running short of time. So here is the first question.
Yes.
Someone says, if I'm interested in training a classifier such that it is okay if it classifies English text as Korean, but it is very undesirable if it's the other way around.
Yes.
How do we integrate this kind of business logic into this model? And can we modify the loss function in some way? And how does that fit in your overall setup?
Right. So this is actually a particularly simple problem because you can solve it using standard utility-sensitive classification itself. Let's go back all the way to utility-sensitive classification. Right. So you can have instead of the sky, cloud, and mountain, imagine it's Korean, English, and Hindi. Right. So you can have Korean, English, and Hindi. Right? We can have that Korean being classified as Korean is 1 point. Korean being classified as English is, let's say, 0 points. English being classified as English is 1 point. English being classified as Korean is, let's say, instead of 0, what was the, I think there was one other thing, right? So you can have one, instead of 1, 0, 0, 1, you can have things like 1, half, 0, 1. Right? So that would, you are naturally penalizing Korean being classified as English more than English being classified as Korean. So both, ideally you would want to get Korean as Korean and English as English, but by just incorporating instead of a 1, 0, 0, 1, you have a 1, half, 0, 1. What I'm saying is, if you classify Korean as English, I'll still give you half a point. But if you classify English as Korean, I'll give you 0 points. So this is an easy way to tackle this. But of course, you can use more sophisticated ways also.
Okay, thank you. So one more question.
Yes.
Are there practical examples where the classes have a hierarchical structure, and how do you evaluate them in your setting?
Right. So typically, a lot of these, for example, if you have classes in a hierarchical setting, you can incorporate it in the loss matrix again, or the evaluation metric, or the utility matrix again. But in some situations, you might not want to do that. You might want to use what are called hierarchical F measures. Right? So I've told F measure in this setting where it's a flat thing, right? You have n classes, that's just it. But you can, if you have metadata on these classes, it's more interesting to come up with you can come up with better evaluation metrics than just accuracy or F measure. It is possible to do that, and there are hierarchical versions of almost every metric. Yes.
Okay, Harish, in the interest of time, maybe we can stop the live questions here. You can take a look at the questions on the chat, and if there are anything interesting, you can reply to them as well.
Yeah, sure. Thanks, Arun. Thanks for...
Thanks, Harish, for the excellent talk. Thank you very much. So the next talk will start at 5:30. So before that, what we will do is, like the last break, we will show a couple of posters, so which may be of interest. So let me share my screen. Yeah, as I had already passed on the link, so here are some posters that we have chosen for day one. You can go and take a look at them whenever you have some time. So what we will do in this break is display one of the posters by Dev Sheth Yashpal. So this poster is on. So he's a third year dual degree in computer science and engineering IIT Madras student, and so here is a quick video about what he wants to discuss. So let me play that.
Hey everyone, I'm Dev, and I'm here to talk about this, which is an algorithm we use pairwise comparisons because they are much simpler than giving a complete ranking, and they are much more accurate than individual ratings. We consider the shoestring budget because it is much more practical. The budget is typically CN, SC is a small constant, say 2, 3, 4, and N is the number of items. We use a popular spectral ranking algorithm called matrices. So what is Paris? In the first phase initialization, we use n-1 comparisons to initialize our Markov chain. In the second phase, instead, we vary the most disruptive pair, incrementally update the Markov chain, and keep doing this until the result is placed. We perform experiments on both synthetic as well as real organisms in large standard weightage aggregate and observe that our algorithm is better than the state of the art, significantly in almost all cases. Look at top K recovery and theoretical guarantees of our algorithm.
Okay, so that was a quick introduction to his poster on active learning. So if you did not hear that well, you can again go back to the YouTube link. It's available in the web page. So let me continue with one more poster. So this is by Preksha Nema. She's a PhD scholar in the Department of Computer Science and Engineering at IIT Madras. And let me play the video that she has for us.
Automatic question generation, so where you have been given a piece of text and a possible answer like Napoleon here, and you want to generate one possible question which could be who liberated Warsaw in 1806. So the way such systems are currently modeled is that you have an encoder which tries to abstract out the information between the passage and the answer interaction, and then you try and generate the questions one word at a time in one single pass, which is called a decoder. So now, unlike humans, they don't revise the question that has been generated in multiple revisions, and therefore it could be either incomplete or incorrect. So now we tend to mitigate this problem by decoding it one more time, where the new refinement decoder takes into account the passage and answer, and along with that, it also takes into account what has been generated in the first pass. So now here you can see that the new question that has been generated has been corrected by saying whose army rather than who liberated Warsaw. So now, since we are anyways generating it in two passes, we can make sure that the second pass is better either in terms of fluency or answerability, or it should be more original as compared to the source document that you have given. So the way we do that is we add a reinforced loss on the second decoder as compared to the first decoded sentence, which will be the baseline, and you try to have a reward signal of blue or answerability. Thank you.